Uh, Today's topic is numerical differentiation and integration. So, differentiation and integration is one of the the two of the uh, key mathematical uh, methods we use uh, in physics. It is very important uh, if you try to solve uh, physics problems, even a simple physics problem. Uh, you may use differentiation or integration. Uh, so you know that the first derivative, right? The first derivative is the uh, first derivative of a function represents the rate at which the function changes with respect to some variable. So you know the velocity, right? Velocity is the first derivative of the position or the displacement with respect to time. Now, you also know that the acceleration is the first derivative of the velocity with respect to time, and the force is directly proportional to the acceleration. Therefore, you can calculate force applied on some object using the acceleration. So for that purpose, if the velocity is given or the function of the velocity is given, you need to calculate the first derivative. So likewise, even in a simple physics problems, you are using the differentiation, and you know that you can use integration to calculate the area uh, uh, area of a function between some points in the space. So differentiation and integration are key mathematical methods we use. Two of the key mathematical methods we use in physics. Now, in the numerical differentiation, we try to estimate the derivatives of a function using discrete data points. Now, when I'm saying discrete data points, that means let's say our independent variable is x, and the x changes with some step size. So let's say x starts from 0. X starts from 0, and we add some small step size like 0.01. So if the starting point is 0, the next value is 0.001. The next point is 0.002. The third point is 0.03. Likewise, we divide the x axis into small parts. So we are using some approximated function, or the function for estimating the derivatives. So here I'm discussing about the first derivative, and there are three popular techniques we can use. The first one is forward difference. the second one is backward difference, and the third one is central difference. So in the forward difference, the first derivative is approximately equal to f of x plus h minus f of x over h. So h is the step size, x is some values in the x-axis, and x plus h is this x value plus the step size. And we have to divide this by h, the step size. In the backward difference, the first derivative of x with respect to x is approximately equal to f of x minus f of x minus h over h. In the central difference, first derivative of x, first derivative of f of x is approximately equal to f of x plus h minus f of x minus h over h. So we have three different methods, and we can calculate, or we can estimate the first derivative using them. So you are going to work on all three techniques for the assignments. However, I will discuss about the theory behind the forward difference method, but you need to work on all three methods for the assignments. Okay, first at all, I'm going to show some examples for all three techniques. Here I am consider a function f of x, which is equal to sine of x. So sine of x is the function we are going to differentiate with respect to x. So we want to estimate its derivative at x is equal to pi over r, pi over 4, using a small step size h is equal to 0.001. So we need to calculate the first derivative at pi over 4 with the step size of 0.001. So what we are going to do is we are substituting x and h with these numbers. So the function is sine, and x is equal to pi over 4 and h is equal to 0.001. So if you plug them here, you will get a 0.707 for the first derivative of sine of x. And from the backward difference, if you do the calculations, you will get 0.7071. And from the central difference method, you will get the same values. And you all know that the first derivative of sine of x is cos of x, right? So here you will you see the analytically how to solve the first derivative using analytical methods. So it is cos of x, and if you calculate the cos of pi over 4, the value is 1 over square root of 2, and that is equal to 0.7071067. So we got almost the same number. You can calculate the error. So using this example, you see that all three methods are working. But when the function is more complicated, there may be higher deviations from the true value, because this is the true value and this is the estimated value. from the approximated functions. So anyway, so you can see that somehow these three functions are working well for these kind of functions. Now, even though since these are since we are trying to approximating the value of the first derivative, we need to find the or we need to have some idea about the error associated with these approximations. Since these are approximations, there should be some error between the approximated value and the true value. Like this is the true value, which was calculated using the analytical method, and this is the approximated value. There is some error. So we need to have some idea about the error associated with the techniques. So to explain that, I'm going to use the Taylor series. Taylor series is a mathematical technique used to approximate functions that are difficult or impossible to express in a closed form. So so we can approximate functions using Taylor series. So this is the expression for the Taylor series, and here we expand the function, which is f of x, and we calculate the summation from n is equal to 0 to infinity, and within the summation you can see that it has the derivatives like first derivative, second derivative, third derivative, up to infinity. Okay, and here here you can see the factorial n at the denominator, and this one is x minus a to the power n. So n represents the index for the term, each term within the summation. Okay, now here this a, what is this a? So when we expand the function using Taylor series, we are doing it around some value. Okay, around some x value in this expression. So that center value is represented by a in this expression. Then if I write this without the summation mark, or if I expand this, I get f of a, that is the value of the function at this center value, and then we have the f prime of a, that is the first derivative at x is equal to a, and we have x minus a here, and plus a second derivative and associated terms. So you can see that the factorial 2 is here because of this, and then we have the third derivative and so on. So you have to understand that this factorial f represents the derivative. So first derivative is represented by factorial f, second derivative is represented by double factorial f, then this is the third derivative, like that. Okay, now what I'm doing is I replace I replace x with x plus h, and I write the Taylor series around x, some arbitrary x value. So so if I write it in this way, I get h instead of x minus a. So a is x now, x is x plus h, therefore h is equal to x minus a. So I'm getting this expression. And then we rearrange the terms in the Taylor series expansion in this way. So f of x plus h minus f of x is equal to sum of these terms. So all these terms have the some order of derivative with some kind of order. So we have and then we divide this by h. All both sides are divided by h, and we have this expression. And by neglecting these higher order terms, the terms with h and h squared and so on, we get f prime x, f prime of x is equal to f of x plus h minus f of x of h. So we got the expression for the first derivative in the forward difference method. Okay, so that is the derivative of the forward difference method. And now I'm trying to find the truncation error associated with this approximation. So truncation error refers to the inherent inaccuracy introduced when using the forward difference method to approximate the derivative of a function. Actually, this can be generalized for any method, okay? Any method associated with the Taylor series or approximation. So for our case, we are discussing about the forward difference method in this lecture. So we can write the Taylor series in this way. I was showing it before, and now we think that, let's say we think that we can approximate this f of x plus h using the terms up to the h squared term. That means up to here. So what we do is we get rid of all the other terms in the Taylor series, because remember that the Taylor series is written with the terms up to infinity, right? H to the power infinity. But now what we are doing is we are getting rid of all the higher order terms greater than h to the power 2. So we approximate f of x plus h using this function. So you can see there is an error because actual Taylor series has more terms, but we are considering only a few number of terms. Therefore, there is an error, and this truncation error is given by exact value minus approximate value. For this example, the truncation error is given by third derivative of the terms associated with h to the power 3 and the terms associated with higher order of the h. So this is the expression for truncation error for this example. Okay, don't confuse with the forward difference method. This is a different example, and for this example, this is the error term. So remember that h is a very small number, right? H can be 0.01. So since we are considering the power of the h, when the power is increasing, these terms becomes negligible. Let's say, so for this one it is 0. If h is 0.1, this is 0.0.01. There are 3 decimal places for this. This one will have 4 decimal places, and the other higher terms will have more than that. So these terms becomes negligible. Therefore, we are only considering the first term. That is the most influenced term in the truncation error. So the order of accuracy of a numerical method indicates how the truncation error decreases as the step size h decreases. If the leading term of the truncation error is proportional to h to the power p, the method is said to be of order of p. That is denoted by O of h to the power p. So in this example, you can see the leading term is h to the power 3, because these are negligible. The high order terms are negligible. Therefore, we say that this approximation has the truncation error with the order of 3, and it is denoted by O of h to the power 3. So that is the truncation error. Now, what is the truncation error for the of the forward difference method? So let's see how we derive the expression for the forward difference method. Now, this is the Taylor series, and we simplified, or we rearranged the Taylor series in this way, and then we derived this expression for the first derivative. Okay, now you see that we neglected these terms. We neglected the terms associated with h associated with hn, associated with h, right? Because of all the terms we neglected have h. So we neglected these terms. So this is the expression for truncation error, and this is the most influenced term, or the leading term in the truncation error expression. Therefore, the t of the truncation error of the forward difference method is of the order of h. It is denoted by O of h. So next, so there are several other methods you need to study for the laboratory assignments. However, I'm not going to explain everything in this lecture, but I'm trying to help you to understand the numerical differentiation and integration. Now I'm going to explain one of the simplest and also the popular methods in the numerical integration that is called a trapezoidal rule. It's a numerical method for approximating the definite integral of a function. So it approximates the value of a definite integral. That means if we have a function called f of x, we are integrating it with respect to x from a to b. This is a definite integral because we have some boundaries for the function when we integrate them, and it is approximated by this expression over here. The right hand side has x over 2 times f of a, that is the a is the starting point of the x, the range where we integrate this, and this is the endpoint b. So we have f of a and f of b, and then we divide that into parts, into intervals. So let's say we divide this into n parts. So the step size is b minus a over h. That means the difference between two numbers in this x values is h. So each element or each x value is given by a plus ih. So the values as for the integrals associated with each xi is given by sum of 2 times sum of f of xi, and the summation is performed from I is equal to 1 to n minus 1. Okay, so I'm trying to find the truncation error associated with this trapezoidal rule. So so here we have the general expression for the Taylor series, and we are going. So you will see that this Taylor series is written around xi. So the middle value is xi, the centered value is xi. So and then we integrate f of x from xi to xi plus 1 with respect to dx, and so we can integrate each term. So each term in the right hand side. So this is the first term, and this is the second term, and this is the third term, and so on. So if I integrate the first term, I'm getting f of xi times f of x I plus 1 minus xi. So you know that this is a constant because we substitute x with xi is some constant value. So therefore, after substituting x with xi, we are getting some constant. So we are integrating a constant over here. Therefore, the integral will be x, and since this is a definite integral, we get xi plus 1 minus xi. And xi plus 1 minus xi is equal to the step size. That is the difference. H is the difference between two consecutive x values, and we get f of xi times h. And this is the result for the second term, the integral of the second term. So f prime of xi is the first derivative of f of x and at x is equal to xi. So it is a constant, and we are actually integrating this part, x minus xi. If we integrate it, we get xi plus 1 minus xi to the power 2 over 2. So finally, we get f prime of xi time h to the power 2 over 2. So this is the result. Likewise, we can calculate the integral for all the terms in this expression derived using Taylor series. So finally, this is the expression we found for the integral of f of x between xi and xi plus 1. So this is the correct or the true expression for the integral. And we let's label it as equation A. And then again, I can write Taylor series for f of xi plus 1. What I did is I have this expression over here, and I substitute x with x with xi plus 1. So if I write with xi plus 1, I get this expression. Since h is equal to xi plus 1 minus xi, these terms can be substituted with h. So we replaced these terms, and I got this expression over here. So we have xi plus 1 at the left hand side, f of xi plus 1 at the left hand side, and f of xi at the right hand side, and other terms. And this should be xi. Okay, this is a mistake. Okay, so since trapezoidal rule for the interval of xi and xi plus 1 is given by this expression over here, I rewrite this expression in this form. So I get this, and I call it equation B. This is the approximated expression for the integration, and this is the true expression. So we have true expression and also the approximated one. So the truncation error is the difference between the actual one, or the true value and the approximated value. So I can calculate the difference between these two, right? From equation A and B, and then if I simplify this, these f of xi and f prime xi terms will be cancelled out, because these are in the same values are in the both expressions in this blue and red. So finally, you can show that the leading term of the error is associated with f double prime, or the second derivative. Therefore, for single interval, the integration of single integral of for single interval is proportional. The truncation error of the integral of a single interval is proportional to h to the power 3. So the error is with order of h to the power 3 for single interval. Okay, this is not the whole interval, whole range, because you know that we are integrating the integral, the function from a to b, but we calculated the truncation error for single interval. It has the truncation error of order of h to the power 3. So, however, we need to calculate the truncation. We have to find the truncation error of the whole range. For that purpose, we calculate the sum of all the truncation errors within this range, that is from A to B. So this from I is equal to 1 to n, and we have this h to the minus h to the power 3 over 12 times sum of f double prime of xi. Now, mathematically, it was proven that this summation mark can be replaced using some value, and that value is equal to the average of this second sum of these second order terms, second order values, second order derivatives of a function. So we calculate the average, and then we have this nh n times h to the power 3 in the numerator, and nh means b minus a. Therefore, we can show that the truncation error can be approximated with some constant times h to the power 2. Therefore, the error in the trapezoidal rule is proportional to h to the power 2. So the truncation is the order of h to the power 2. For a single interval, the truncation error is proportional to h to the power 3. However, for the whole range, that is from A to B, the truncation error is proportional to h to the power 2. So there are two types of truncation errors with two different orders when we consider single interval and the whole range. Okay, that's all I have for today. So all of you can start working on the assignments now. Those are available in the LMS. And Milash or other demonstrators, do you have anything to say to the students?
So there are some small things to tell, rather small feedback of the last week assignment. That's all, sir.
Okay, so you can go ahead and